My name is Jinya Lin from the University of Hong Kong. I will introduce our paper, Optimal Differentially Private Algorithms for K-means Clustering. My co-author is Jinya Lin. Privacy in data analysis has gained more and more attention from both academia and industry. There is a quite standard privacy concept called differentially private. It has also been used by some big corporations, such as Google, Apple, and Microsoft. Let's see the formal definition. We say a randomized algorithm M is epsilon delta differentially private if this property holds for any subset S of the function range Q and for all neighboring data set D and D prime. Here, neighbor means that D and D prime have only one different item. We denote it as X. Then the probability of MD in S is less than or equal to e to epsilon times the probability of MD prime in S plus delta. Let's see this plot for understanding. It's for a simple case with delta equals to 0. The output distributions of MD and MD prime is almost similar, with difference at most e to epsilon. So when we observe a series of output S, we can distinguish whether the input is dataset D or D prime. Therefore, we cannot get the real value of individual X. Then the privacy is protected. We focus on K-means clustering, one of the most popular and well-studied clustering algorithms. Given a dataset D, it aims to output a set of K centers with the minimum cost. The cost is defined as the sum of Euclidean distance between each data point xi to its nearest center cj. In the following, I will use this delta k square to denote the optimal cost, that is the minimum cost. So like in this example, we want to find these three centers. Given any set of centers C, we can calculate the cost of the dataset D as a criterion for this center set. The smaller cost, the better. In this paper, we also consider another criterion called the Wasserstein distance. Given two sets of centers C and C hat, the Wasserstein distance is the L2 distance under the best permutation. See this example with k equals to 5. Then the best permutation can be presented by these 5 dashes. So the Wasserstein distance can be calculated by the length of these 5 dashes. If we use C to denote the optimal center set, then for any other center set C hat, we can calculate the distance between them as another criterion for this C hat. The smaller distance, the better. Next, I will show a good property of a data set. We say it is phi square well separated if delta k square is less than or equal to phi square times delta k minus 1 square. Here, delta k minus 1 square is the minimum cost for k minus 1 means clustering, and phi square is a small constant. See this example. We have 3 datasets here. If we consider for 2 means clustering, only D1 is well separated. Intuitively, this is correct, and it can also be proved by definition. Look at D1. The cost for 2 means is much smaller than the cost of 1 means. But in D2 and D3, the cost for 2 means is not much smaller than the cost of 1 means. So we say D1 is well separated. In a well-separated data set, the layered type method can lead to a near optimal solution efficiently. Why we consider well separation here? This is because that in a well-separated dataset, points are located around their centers compactly. So changing one point will not change the optimal centers significantly. And formally, we say this is small sensitivity, and this is very important for epsilon delta differential privacy. But this property may not hold for non-well-separated dataset. Say this non-well-separated dataset, we can construct a neighbor of it with only one different point. Then the optimal clustering can change a lot, from the pink to the orange. This is a large sensitivity. So far, I have shown two objectives. One is small k-means cost, the other is small Wasserstein distance. It is easy to prove that small Wasserstein distance implies small k-means cost. For the other direction, it needs some conditions. For example, well separation. See this non-well separation example. The left one is the optimal clustering. Look at the right one. The cost is also small, but the distance between the pink and the orange is large. In the following, I will show our results for the small Wasserstein distance objective and skip the k-means objective part. There have been lots of work about epsilon delta differentially private k-means algorithm to use the Wasserstein distance on well-separated dataset as objective. Nissim et al. Firstly gave a sample and aggregation framework. It shows a private algorithm with additive error O phi square root kd over epsilon, where d is the dimension of the dataset, and epsilon is the parameter of privacy. Then they introduce a private one-cluster location algorithm. This algorithm can be applied into the sample and aggregation. If we combine these two works, we can get a private algorithm with error O phi square root k log n. Then they introduce a better one-cluster location algorithm, which yields a better private k-means algorithm with error O phi square root k. We improve the previous result. To keep epsilon differentially private, we give a private algorithm with additive error only phi square, reduce the dependency on root k. We also prove this is tight. Next, I will briefly show our technique. Let's firstly review the sample and aggregation framework. Given a dataset D, firstly, partition it into T subsets randomly and evenly. Then apply the approximate k-means algorithm to get T sets of centers. So we can get a center set of size kt. In detail, C1 contains k centers, so as any other center set Cj. Then we use these blue stars to denote the optimal centers for the original dataset D. By the well separation condition, we can get that for each pair of blue stars, they are far away. Then combine with the sample property. For each clustering with the same color, they are also far away. Combine the previous result of the previous three work, we can partition these kt centers into k clusters, and each of radius O phi square. Then we can use a private location algorithm k times, each time to find a center close to each cluster. So we can get k centers finally, and with the arrow O root k phi square. Then I will show our improvement. We prove and apply some other good properties of this centered set. Firstly, there are no outliers. All these points are located exactly in these clusters. Secondly, we have k clusters here, and in the size of each cluster has the same size, t. Thirdly, we prove a smaller Wasserstein distance. See this smaller Wasserstein distance first. By the previous idea, we have k clusters here, and in each cluster, the distance between each center in Cj and the center in the optimal set C hat is phi square. We then prove a better bond, the Wasserstein distance, that is, combine this k distance is also O phi square, rather than root k phi square. So given this better Wasserstein distance bond, we want to get a better solution. For example, we want to apply the private location algorithm only once and find the k centers simultaneously. To find these k centers simultaneously, we can treat it as one point in another metric. For example, to project these k centers, say j, into in d dimension into one point in kd dimension. The problem then becomes to how to do the projection from k points to 1 points. There is a quite straightforward idea to find a sorting of these k points. We can list the k value of each point, then list these k points one by one. So we can get a kd tuple, then treat it as a point in kd dimension. The problem then becomes to how to find this sorting. It should keep one property, that is, for any two sets of clustering, the Wasserstein distance before projection should be equal to the Euclidean distance after projection, because the private location algorithm is applied in the Euclidean distance. Then these two properties can be used here. We have k clusters here, and each cluster has the same size t, and for any center set Cj, it can be partitioned into k clusters. So for these k clusters, we give it a label from 1 to k. Then for each clustering, this label will define a unique permutation. We can also prove that it's the best permutation. Recall the Wasserstein distance definition. It is actually the Euclidean distance under the best permutation. So we can do the projection by these labels. Just sort these k points and list them one by one. Go back to the algorithm. We have t sets of centers here, and the Wasserstein distance between each Cj to optimal center set C. Go back to Okay. Go back to this algorithm. We have get T sets of clusters, and the Wasserstein distance between each Cj to C star is phi square. Then we can do the projection. To project these T sets of centers to T points in Kd dimension. We can prove that all of these T points are in a cluster with radius phi square. Finally, we can use a private location algorithm one time to find a point close to this cluster. Finally, projected back, we can get K centers in D dimension. Therefore, we have get a private solution with arrow phi square in Wasserstein distance. And next, I will show our lower bound. In many differentially private algorithms, when a dataset grows large, the impact of one single point gets smaller. Formally, we say the sensitivity gets smaller. So, when a dataset gets large enough, both the sensitivity so when a dataset gets large enough, both the sensitivity and error will diminish. We want to ask that let me repeat it again. Yeah. When a data set gets large enough, both the sensitivity and error will diminish. So we want to ask that, is this intuition correct here for this k-means clustering problem? Unfortunately, the answer is no. For any k, we can construct a phi square well-separated data set whose local sensitivity is at least phi square. Where the local sensitivity is defined as the maximum distance between the optimal center set of D and the optimal center set of its neighbor, D prime. Recall the definition of epsilon delta differentially private. We need to guarantee that for any two neighboring data sets, the outputs should be indistinguishable. However, here we have two neighboring data sets with distance at least phi square. So to make them indistinguishable, the error term omega phi square is needed. Next, I will show our construction. Say two clusters for example. We have two large clusters here, each of size n, and in the middle between them, there is a small cluster. At first, the optimal clustering can allocate it to either the left or the right. Then, if the left cluster gets smaller, this green cluster will be allocated to the left. So we look at dataset D3. If this green cluster goes to the right, the optimal clustering will allocate it to the right cluster. Based on this idea, we can construct a neighbor of S3 by delete one point from the left cluster. Then there is a chance that this green cluster will go to the left. So we can prove that the size of this green cluster can be phi squared times n. So the y-sustain distance move is at least phi squared. The key idea of the construction is that although we only delete one point from the left cluster, the allocation of this green cluster can all be changed. So the sensitivity is larger than our intuition. Based on this idea, we can construct instance for any k. We have k large clusters here and k-1 small clusters. At first, these small clusters are allocated to the bottom clusters. Then, if we delete one point of the top, all of these green clusters can allocated to the top. We can also prove that the size of each green cluster can be phi squared times n over k. So the y-sustain distance move is also at least phi squared. Given this phi squared lower bounded sensitivity, we can get the phi squared lower bounded arrow. So far, I have shown our results for the y-sustain distance objective with optimal arrow term sigma phi squared. And for the k-means objective, in our paper, we also designed a private algorithm with additive arrow alpha n, where alpha is any arrow term. There's still some work can be done in the future. For example, in our algorithm, the constant is large, so can we reduce it to make it more practical? Secondly, k-means problem has a strong connection to k-median problem. So can this algorithm to be extended to k-median problem? We can think about that. And my presentation is done. Do you have any problem?
Thanks for the nice presentation and for keeping the composure. There's so many glitches. Any question?
So you have a lower bound and upper bound, but these are asymptotically, right? And you said that the constant in your algorithm is very large, right? So in the lower bound, the constant no, sorry.
Yes, constants means that the assumption for the data set, we need the data set is very large. It has some constants depends on phi squared, epsilon, d, and a large constant.
So in practice, in running k-means, you would have to actually tune the parameter k. So it seems that you have assumed that k was known in advance. What happens when k is not known, right? And you have to learn k. Would all of these algorithms still work if you have to find what k is?
Yes, if k is if k is unknown, our algorithm also works. Since this is also private algorithm and our arrow bound depends on phi squared, so even we don't know k, we can use this algorithm, but maybe the arrow we can't guarantee it. But it also works.
Yes. So